tangents today because it was, but you didn't have to use it. So it sounds familiar because when we went over chapter 8 with SOHCAHTOA, you had tangent of certain things in your right triangles. Okay, but these are tangents to circles. Okay, so let me make sure my pen has ink in it. Okay. So a tangent is a line in the same plane as a circle that intersects the circle in exactly one point. Okay, so this line intersects your circle in just one point. That point is called a point of tangency. Okay, so that one point is the point of tangency. So on the right here, we have line AB, right? So line AB is tangent to circle C at point A, and point A would be your point of tangency. So that is where this line and this circle intersect. It's only at that single point. Okay? So it doesn't have to be just a line. Okay? So line we indicate with arrows. It could also be a segment. Okay? So it has endpoints. Or it could be a ray. So it has one endpoint and extends further with the arrow at the end. Okay? So those are also called tangents. So it could be a segment or ray as well as a line. So we do have common tangents. A common tangent is a line, segment, or ray that is tangent to two circles in the same plane. There are two examples below here of common tangents. So the first one on the left there, you have circles F and circle G. Okay, line L is a common tangent because it's tangent to circle F at this point right here and tangent to circle G at this point right here. Okay, so that same line can be tangent to two separate circles. Okay, same thing in that example at the right there, except their point of tangency is the same for both circles. Okay, so it has that one point of tangency with that common tangent. Okay, so we're looking to see where that line hits exactly one point. So we are going to draw in the common tangents in the examples below. That's why I had you pick up a ruler so you can draw some nice straight lines. So, quiet please. So letter A, there are two common tangents for those two circles. Okay, one, I could put my ruler this way. Okay, so I can draw in a straight line that hits both of those circles in one point. Okay, so that would be one common tangent. There's another one. Where do you think that one is?
On the bottom.
On the bottom. Okay, so on the bottom right here, you can draw in another one. So that hits both circles at one point. Okay, so those are your two common tangents for letter A. All right, letter B. Again, we're going to draw in the common tangents for this one. This one has 4. Okay, so there are 4 lines, tangent lines, that we can draw in. So the tops have a tangent line, right? And the bottom. Okay, so I have one right here. I have one on the bottom. Where would another one be? Yes. Okay, they make, the last two make X's through the middle of both of those. Okay, so I could make one here. Okay, so it hits the smaller one at this point, the larger one at this point. And then I can make another tangent the opposite direction to make that X shape. Again. Okay, so shh, quiet please. So these two circles have 4 common tangents. Okay, the last one. Where do you think a common tangent is? Right at the right where they intersect each other. Okay, that's the only common tangent for this one. Okay, at that point of intersection of those two circles. All right, so those are your common tangents. Okay, so common tangent where that line hits both circles at one point of tangency. So, looking forward here, the shortest distance from a tangent to the center of a circle is the radius drawn to the point of tangency. Okay, so in this theorem box right here, it says in a plane a line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. Okay, so it will be perpendicular. So looking at the picture, line L is tangent. Okay, at point T. That's your point of tangency. The radius drawn in to your line tangent, that shortest distance, okay, would be perpendicular. Okay, so if I want you to find the shortest distance from the center to your tangent line, that's going to be the radius that is perpendicular to that tangent line. Okay? So we're going to go through examples of this on the back. So on the back, example 1, segment JL is a radius, okay, of circle J. We want to determine whether KL is tangent to circle J. Okay, so JL right here is a radius. Now, if this line is tangent, then that radius has to be perpendicular to that tangent line. Okay, so that means it has to make that 90-degree angle. Now, what does that look like with all 3 lines? It looks like a what? A triangle. What type of triangle? A right triangle. Okay, so what I'm going to do to show if this is a tangent line is use the converse of the Pythagorean theorem. Okay, so that is using c squared compared to a squared plus b squared. Because we want to see if those two quantities, so c squared and then a squared plus b squared, are equal. If they're equal, then that is a right triangle and it's perpendicular. If they're not equal, then that line KL would not be a tangent. Okay, so for my c squared value, right, we would need this entire line here. This segment from point K to your circle is 9. What is this segment right here? 8. Because that's a radius. So I need to add those two together to get the entire segment, which is 17. Okay, so since that would be considered the hypotenuse of this right triangle, you plug it in for your C value. So we would have 17 squared compared to 15 squared plus 8 squared. Okay, so 17 squared is 289. 15 squared is 225. And 8 squared is 64. So I just want to add these two together on that right-hand side. So I have 289 compared to 289. Now these two are equal. Since they are equal, that means JL is perpendicular to KL because this is a right triangle then. Okay? Meaning I can say KL is tangent to circle J because that's what it was looking for. If you do your problem and stop right here, you're not answering the question. This work shows that this is correct, okay? But this is what you need to answer, okay? So you can say KL is tangent to that circle because those two are equal. Okay? Questions on why I did any part of that example? Do you know why I'm using the converse of the Pythagorean theorem?
Yes.
Okay. Then I want you guys to do example 2. Okay, so you're doing the same process. You want to see if GH is tangent to circle F. So you need to use the converse of the Pythagorean theorem to show if it is or not. Is it drawn to scale? No.
Yeah. So it could both be this little and then 6 is like this. 64 plus 100. That's 18 squared. 324. It's not. What's 2 or 8? How about 6 squared and 6 squared plus 8 squared? It's 18 squared. Space 6 squared. No. Plus 8 squared. Okay, so and then 324. The underscore thing. 36. Done. Don't distract me when I'm doing those.
Why is this going to go on?
Before I get my from PC, it's just
Green apple.
So then this would be a squared plus b squared, right?
All right, so looking at example 2, so GH is this line right here, and we want to see if it's tangent. You can come up here and grab on here. We want to see if it's tangent to circle F, so we want to see if it's perpendicular with that radius. So point H to this point right here is 12. And this point to point F is 6. So I need the entire length of F to H. That's 18. Okay? So that would be my hypotenuse in this right triangle. So I can take 18 squared, compare it to 8 squared plus 6 squared. Okay, 18 squared is 324, compared to 64 plus 36. So we have 324 compared to 100. And that is not equal since 324 is greater than 100. So since they are not equal, I would say GH is not tangent to circle F. Okay, questions on example 2? For your assignment, the 3 problems on top, okay, those lines are tangent. Okay, so they are tangent. So you just need to use the Pythagorean theorem to find that missing side. Okay, you're not comparing them. Okay, in the directions it says assume that segments that appear to be tangent are tangent. So segment JK in number 1 is tangent. That means HJ and JK are perpendicular and form a 90-degree angle. So you can use the Pythagorean theorem to find the missing side. Okay, that's true for numbers 2 and 3 as well. So for those ones, again, they are equal. You're going to just use the Pythagorean theorem. For 4 and 5, that's where you're going to compare. Okay, so those ones you have to see if they are tangent like we did in examples 1 and 2. And then on the back is just a review of some other chapter 10 stuff that we've done.